Hey everybody, and welcome to Modelscapes Introduction to Sparse Modeling in R. My name is Krista. I'm a Modelscapes postdoc at the University of Montana, and I'm an aquatic ecologist by training.
Everyone, my name is Saeed Olaide Jimo. I'm also a postdoc with the Modelscape Consortium. I work with Lachlan Research Lab. I'm a plant ecologist by training.
And I'm Amy Patterson. I'm also a Modelscapes postdoc. I'm currently a postdoc at the University of Maryland, and I'm a theoretical ecologist by training.
So, the three of us are going to walk you through this workshop from this introduction through the hands-on portion of the code. Please note that to participate in the hands-on portion, you're going to need an up-to-date version of R and RStudio installed on your computer, as well as some specific R packages. These packages and the code and data that you'll need are all linked in the video description below. The Modelscapes Consortium is not only the University of Montana and the University of Wyoming, it also includes the University of Nevada, Reno. And there are more links in the video description if you want to learn more about what we've done. Our goals for this workshop are, perhaps evidently, to introduce you to sparse modeling by giving you some background information. What is it? When is it useful? We'll be focusing on two of the many sparse methods, LASSO and SuSiE, which will include a brief introduction to the two approaches and some hands-on practice running these analyses, as well as a discussion where we share LASSO and SuSiE results. And overall, the goal is to make it easier for you to incorporate sparse methods into your own work. So you've probably seen this quote by George Box before: all models are wrong, but some are useful. What that's getting at is that there is no way to perfectly capture reality in any model. That would be like having a one-to-one map, right? Where a map is life-size. It's got a ton of data, but it's really not usable. Levins in 1966 came up with this tri-Venn diagram. These are the three things that people tend to want in their model. Realism, does your model capture the essential features of the system? Precision, does it do that accurately or precisely? And then generality, can you apply it across different contexts? Can you use it on different data than you use to train the model? And Levins also came up with the idea of trade-offs. You can't maximize all of these things. You have to determine which are most important for your question and your results and your data set. Levins wrote this in 1966, and computing power and speed has increased exponentially. My laptop has more power and speed than computers tended to back in the 60s. We also have a ton of ecological data, from satellite imagery, fine-scale climate data, high-frequency sensors. We have more ecosystem data than ever before. Does that mean that we can come closer to that sort of overall goal of maximizing realism, precision, and generality in our models? Can we do it all? Maybe. The caveat is because traditional models can really struggle with big data. They're really challenged to ID key covariates when there are a lot more covariates than observations, which is common when you have these really large data sets. Traditional models tend to overfit, which means they select both important covariates and white noise in the data set, adhering really precisely to the training data or the data you used to run the model the first time, but then they don't do well on new data. And as a result, they can provide the wrong answers and might fail completely if you use them on a different data set, for example, a different site or a different year. Clearly, this is a problem. Sparse methods were developed to help solve this problem. So sparse means of few and scattered elements, and a sparse problem is when you have just a few important covariates scattered about a set of a lot of unimportant ones. And sparse modeling methods attempt to select only these important covariates. To help visualize this, you can think of this graph where each row is an observation, and those are limited, and each column is a covariate, and that list goes off the screen. Only two in this example of the covariates are important, the ones in purple. Now, sparse methods introduce a penalty of some sort to covariate selection, and that helps them select just the important ones. This increases model interpretability and reduces overfitting. It winnows out that white noise and focuses in on the covariates that are truly important for your system. We've been pretty abstract so far, so here's some concrete examples in ecology. So the classic example is trying to predict phenotype from genotype, because there are literally millions of potential covariates. Every single DNA base pair in a genome is a potential covariate. With population density in the environment, if you're trying to predict the population density of a species of interest as a function of its environment, you're faced with a multitude of potential variables. For example, maximum temperature, minimum temperature, average temperature, maximum, minimum, average precipitation. What season is the precipitation in? Is there a lag? How many impermeable surfaces are there within 10 meters or 10 miles? And so on. Lake color uses satellite-derived parameters, which can be billions of pixels with multiple layers in each pixel. And phenology uses climate data, which again could be weather stations, balloons, buoys, radiosondes, more satellite data, all at really high frequencies. It's easy to become overwhelmed with all the potential covariates that are available. And this is where the promise of sparse methods is so useful. It can help us winnow down our number of covariates and focus on what is truly important for our system. A non-ecology example. So how would you predict the value of a house? This may be something that more of us have experienced. So N, say that's the number of homes in your sample. You're looking at Zillow or something, and you've got 20 or 30 homes. How many things can you think of to predict the value of the house? Square footage, number of bathrooms, number of bedrooms, size of the lot. Does the house have new roofing? How new are the appliances? How new are the fixtures? Is it landscaped? What about the neighborhood? Is it in a good neighborhood or a so-so one? What is the school district like? How does it compare with other houses of its size? Does it have a deck? Does it have a hot tub? And so on and so on. If you think about it for a minute, I'm sure you can think of hundreds of other attributes that are potential covariates. And that encapsulates what a sparse problem is and hopefully how sparse methods can help solve sparse problems. Thinking of science as a model comparison problem, there are three basic goals in science, and your goal in modeling or your goal of your research should determine your modeling approach. This is all based on Trednick in Ecology 2021. If you haven't read that paper, I would strongly recommend it. It's one that Modelscapes we've all found extremely useful. So the three different goals are inference, where you make very few models in advance of the study. One classic example is clinical trials of a drug. You have a set experiment and you run the model and then you run inference on it, statistical significance, R-square values, p-values. Another common goal is exploration, and this is where most studies in ecology fall. You compare your models, either a few or a lot of models, determine which is the best, and use that to generate hypotheses about your data. And finally, prediction is a blend of the two. You use models that get the process correct, but your parameter estimates have been regularized, and so it doesn't allow for strict inference. And it's important to remember not to use inference on an exploratory or predictive model. Sparse methods support both exploratory and predictive research. You can do model selection and estimation in one step, which is useful for evaluating many covariates. You don't have to run multiple models with different subsets. You can do it all at once. Remember that prediction always requires a holdout data set for testing predictive accuracy. A high in-sample R-squared doesn't mean you have a useful model. Also, sparse methods, although they're sometimes accused of this, are not data dredging. Data dredging is when you fit a lot of models in an unplanned way, and then you conduct inference on a chosen model. And again, this is something you do not want to do. Here's why. Friedman, the American statistician, 1983, wrote about this paradox. So what he did was he generated random response and predictor values, 11 observations, and 100 covariates, completely randomly generated. He used model selection to identify the best model. Here we used LASSO. You could use stepwise or any other model selection method. This left him with 5 out of those 100 parameters that were identified as important. That was exploration. Then he conducted inference. He fit a linear model to these parameters and found that all 5 of them were statistically significant. But remember, these are totally randomly selected parameters. They have no relationship to each other. So the take home here, do not conduct inference following model selection. You just can't trust the results. You cannot trust the inference you get out of that. Hopefully that was clear and is something you would never do again. The definition of terms. Before we get into the rest of this, I want to make sure that you see these definitions. They're also available in the workshop materials fact document. Again, these links are found in the video description. Variable or feature selection means determining the covariates that are related to a response variable, choosing your important covariates. In-sample prediction refers to prediction based on the sampled population or the data that's in your model. Out-of-sample prediction is using new to your model data. And regularization for sparsity is adding a penalty term to reduce model complexity by reducing the number of covariates selected. And again, this also helps avoid overfitting. Now on to our statistical methods, starting with the LASSO. LASSO stands for the least absolute shrinkage and selection operator, developed by Tibshirani in 1996. So to give you something that you might be more familiar with as a basis, LASSO is based on ordinary least squares regression with one additional twist. So with ordinary least squares, you're trying to minimize the residual sum of squares. LASSO also does this, and it adds a second term to the quantity that we're trying to minimize, which is the sum of all of the coefficients, the beta, times a control parameter, lambda. So this means that having higher values of the coefficients is penalized because the coefficients are part of this quantity that the method is trying to minimize. As a result, LASSO sets some coefficients exactly to 0. It forces them to 0, reducing the number of potential covariates, because obviously if the variables are set to 0, they're not selected. So comparing LASSO to ordinary least squares, when you have very few data points, here 2, ordinary least squares would just put a line through both points, right? Ooh, we've got a perfect line. R squared of 100, we're done. However, LASSO uses this residual sum of squares and a shrinkage penalty to reduce the slopes for each covariate. So the red line is LASSO, the black line through both points represents the ordinary least squares line. So lambda can range from 0 to infinity. Often you estimate it before you run the actual model using cross-validation to select your best lambda. As lambda increases, the slope of the line gets smaller until it equals 0. So you can see here, LASSO might not always provide the best fit to in-sample data, but it does avoid overfitting. And it tends to provide a better fit to unseen or new data, represented by the gold dots in this figure. On to SuSiE. SuSiE stands for the sum of single effects. It's a Bayesian method, and it uses posterior inclusion probabilities to attain sparsity. So below some probability of inclusion, the model will say that a variable is not included in the model. The algorithm is similar to forward stepwise AIC selection. SuSiE starts with simple single variable models and then builds up to more complex models in an iterative process. And one advantage for SuSiE is the ability for group selection in the case of correlated variables, what SuSiE calls credible sets. This means that it can pick out a group of 2 or more correlated variables and tell you that it thinks at least one of the groups should be part of the model, although it's not sure which one. And the advantage of this is that traditional models would tend to ID just one of the group, while SuSiE explicitly acknowledges their correlation and provides a way of ranking them. So SuSiE works something like this. It's a model that contains just one variable, and since it's a Bayesian model, it calculates distributions for the mean and variance of the estimates, as well as a probability of inclusion. For this example, the probability inclusion is 0.5. Then the iterative part, SuSiE will select the variables, see these starred variables, variable 1 and 3, hold them, and then continue on to recalculate the probabilities based on the residuals from the previous stage, identifying new parameters until SuSiE detects that it has enough. So what is enough? It depends on your data. It also depends slightly on user input. You can input the maximum number of parameters that SuSiE is allowed to select. For example, the default is 10. This does not mean that the model will automatically give you 10 parameters. It means that it won't give you more than 10 parameters, and it will stop at what it feels is the correct number below that selection. For the output, ideally, the SuSiE approach leads to a really clean posterior inclusion plot like this. The posterior inclusion probability is on the y-axis, and it goes from 0 to 1. And only the colored dots have an inclusion probability of 1. For the group selection, this is what it might look like. You've got some variables that still have an inclusion of posterior inclusion probability of 1, and then you have this salmon-colored group. Now, this means that it's likely that one of these variables should be included in the model, but SuSiE couldn't determine which one because they're heavily correlated. So it's identifying them as a group. And their posterior inclusion probabilities add to 1. And again, what you can do is use your knowledge of the system, your knowledge of the variables, and their posterior inclusion probability to make your own decisions about which ones should or should not be included in the model. Before we move on to the data and hands-on section, the last thing I'd like to talk about is some interesting results that the Modelscapes group found when we evaluated several sparse and non-sparse modeling methods. So these results are still really fresh, and the paper is in revision right now, but the preprint is already available online if you'd like to check it out. Again, the links are going to be in the fact document at the end of this presentation and linked below. So there's a lot of information in this paper. We'll leave it for you to discover some of it yourselves, but we will hit a couple of the highlights. So we tested 9 different modeling approaches, 8 sparse methods, and a linear model, which is shown here. And this is an example of how we evaluated each method. And it's also useful for highlighting the typical behavior of linear models. So this plot on the far left shows variable selection. It's divided into causal or non-causal, which we've been here calling important or key covariates, and unimportant covariates in white noise. Causal is important, non-causal is white noise. You can see the black dots are the true estimate. For the non-causal, it's 0. And the other data in this set. And also, you can see there's a lot more non-causal than causal, or unimportant versus important predictors. Our first step in modeling was calculating a predictive ceiling, which is an R-squared of a little over 0.8. So this is an actual best fit based on modeling only the important predictors. The middle plot shows in-sample prediction, which was used on the in-sample set. And you can see it's maybe a little too perfect. It's got a really high R-squared of 0.96, which is higher than the predictive ceiling. And then the plot on the right shows the relationship between actual and predicted values for out-of-sample predictions. Because this model overfit the training data set, the out-of-sample R-squared is much smaller than the predictive ceiling of 0.083. And as noted, the in-sample prediction is much larger. And another figure that we really wanted to show with you, or a result, here's the different methods that we tried. And one of the strongest patterns that we found across all of these methods, sparse and traditional, is that when you increase the number of observations a lot, your models perform a lot better. So, for example, increasing the number of observations to 1,000 or 10,000 improves in-sample prediction, out-of-sample prediction, and also variable selection efficiency. I guess the key point here is while sparse models are effective when you have few observations, it never hurts to have a lot of observations. So next up, Sahid is going to introduce the data set and start the hands-on coding section of our workshop. And again, if you need to, this is a great time to pause and make sure that you've installed all the necessary R packages and downloaded the data set and code so that you can code along with us. Again, these links are in the video description below.
So, the data set that I will be using today is a data set about where dragons live. Dragons are a mysterious creature, and not much is known about where they prefer to live. So today, we are going to analyze one of the few data sets on dragon density. This is actually a really new data, given the recent resurgence in the number of dragons around the world. Since we don't know a lot about dragons, we have a lot of possible predictors that might explain where dragons have the highest density. And these include, but not limited to, price of gold, as you can see here, the price of daggers, density of unicorns, and other mythical creatures, and the distance to the nearest volcanoes, castles, towns, etc. How will we be able to sort through all of these variables to figure out what is really behind all the dragons we have been seeing? This is similar to the scenario Krista printed about you trying to get what is important, when you want to decide how to choose a house. So for this hands-on session, our goal is to practice how to run LASSO and SuSiE analysis using the Dragon dataset that we have. And the main aim is for us to understand the true predictors of dragon density out of all these, available number of predictors that we have to work through. Now let's start the coding session. But before I start, I want to mention that we have a lot of information and notes here in the code. So you don't really have to read every word of it right now, but it's here to serve as a useful guide for you when you code in the future. If you want to follow along, make sure you have downloaded the Dragon dataset, the RMD code file, and open up the RMD file in your RStudio. Okay, now a very quick recap about the LASSO as a way of extensive introduction. So the abbreviation LASSO means the least absolute shrinkage selection operator model. And one merit of this model is that it is flexible because it's very simple and relies on adding just one shrinkage parameter, which is the lambda, to the model. It's also available in many different R packages. So today we are going to be using the GLMnet package, which is one of the most popular packages. There are some notable other implementations, such as the Mono MVN package, and also other packages that you can do more sophisticated analysis, such as Group Lasso. But we decided to stick with GLMnet because it is easy to use and has a built-in cross-validation function that we can use. However, a couple of limitations for the LASSO method are that it can have trouble dealing with correlated covariates. This means that when you have predictors that have strong correlation, it might be an issue for LASSO, and it does not return any standard error values with its estimates, potentially resulting in concerns about how accurate the results can be. In terms of data requirements for the LASSO method, you will need X, which is going to be a matrix of predictor values, where each column represents a covariate and each row represents one observation. So Y is going to be your vector of response variables. For the SuSiE method, it's much of a newer method than the LASSO, and it originally came from the field of genetics as a solution to a classic sparse problem. There's a huge number of single nucleotide polymorphisms popularly called SNPs, in a genome that could affect some phenotype that we care about, for instance, the human height. And only a few of them are likely to have an effect. And so we have huge number of covariates, and we are choosing just a few of them. So SuSiE can actually help us navigate this problem. Another issue with genetic problems is that many SNPs are going to be linked or correlated due to being physically close to a genome. So SuSiE deals with this by using group selection, which groups variables together. It has the capability to group correlated explanatory variables together, um, so that we can understand which of these group of predictors are likely to affect the response variable. Some advantages of SuSiE are that it has high computational speed and powerful Bayesian selection abilities. However, it also has weaknesses. For example, occasional convergence issues is one, a lack of flexibility compared to other Bayesian methods, and issues with group selection due to splitting contributions among several variables, rather. Now, just like LASSO method, you also need a similar data frame to run SuSiE. Now, if you are new to RMD files, that should not be a problem. They are very similar to R scripts. So the main difference is that the code appears only within these blocks of code, sometimes also called chunks, which are interspersed with blocks of writing and explanation in order to make the workflow easy to understand. Outputs also appear in the same pane after running the chunk of codes, so you will see everything in one place. In addition, RMD files can be knitted into HTML files that are ideal for sharing with collaborators. So it's actually a good way of coding when you're working with several other people. All right. So if we go ahead and run the first chunk of code here, it is just going to help us load all the packages that we're going to be using today. And then this next line of code is going to help us load the data set. However, there are three different ways here that you can use to load the data set. So if you clone our GitHub library, or you can use this line. If you have cloned the GitHub library, you can use this line. Otherwise, you can just comment on this line using the hash and use this line of code that allows you to navigate to wherever your data is downloaded in your computer, and you would be able to load the data into your machine. So after this, we're going to go ahead and talk about the data set. But before that, we have a few housekeeping rules here to keep on how to work with the data set. So here we have all our explanatory variables in the data set. If you look at this side of the screen, so this X here, it includes all our predictor variables, which includes variables like the price of cobalt, rubies, dragon scales, swords, and all sorts of dragon-related covariates. And the rows in this matrix are all observations, and each observation has a value for each covariate. Then the Y values or dragon population values are stored in a separate vector, where one vector is for each observation. So just for us to get a better idea of the data set, if we look at this equation, let's go over it. So Y is going to be equal to X1, which is the first column in the matrix, times the beta 1, which is going to be the coefficient, plus X2. X2 is going to be the second column in the predictor matrix, times beta 2, and so on, plus some error that changes with every observation. So in other words, dragon population is going to be a linear function of 74 covariates plus error. And what we are trying to do with this method is to estimate the beta values using the observations. So next, we're going to visualize our data. So let's run the next chunk of code here. So if we run this, yeah. So the first graph shows us the dragon population density in a histogram format. So which means that below here you have the population density, and on the y-axis we have the number of observations. So our values are from -5 to 5, and obviously we all know that population values can never have negative values. So you can see that they are not true population numbers. Instead, these are z-scores. So to get these values from the original populations, we subtracted the mean and then divided by the standard deviation in order to normalize the data. Now, if we look at the second graph here, we've plotted a couple of our covariates against our dragon population density. The covariate values are also normalized into z-scores so that beta values can be easily compared for all the predictors. You can see that there may be something going on with the price of cobalt here with the way the plot is showing. While certainly for the price of hay, we don't seem to have any strong obvious correlation with dragon population. If you're interested, you can look at some of the other covariates by adding in a line of code and rerunning the chunk at the top. So now basically only a few of the 74 potential explanatory variables are going to have meaningful effects because these are all simulated data. We know that the variables we know what the variables are before we start, and we can see these for ourselves. So let's try to run the next block of code and look at the first plot. So here we can see the true explanatory variable values where most of them lie along the zero line, indicating that they are most likely not important predictors of our response variable. Now, if you want to look at the second graph, that is going to tell you the names of the non-zero covariates. So you can see that some of the important covariates for dragon density that we might hope to include in the dragon density model include the price of cobalt. As you can see here, we have the price of gold, we have the time since last crusade, we have days of firestorms, and all the other ones. So one challenge that we face as we go through many analyses is that covariates may be correlated with each other, making it more difficult to select the correct covariates. So before we go on, I'd like us to take on the first activity in the workshop here. Now consider which methods you expect to work best. If highly correlated or uncorrelated variables have large effects. For strongly correlated variables, would LASSO or SuSiE be the best approach? Does it matter if the correlations occur among variables with large effects, between variables with large and small effects, or among variables with small effects? Let's try to move on to our next block of code. So for this, we are going to be making a correlation plot that visually shows the correlation between each pair of explanatory variables so we can see whether correlation will be an issue for our data set. So if we zoom in from here and take a look, we can see that we have some issues with some strong correlations because this dark blue and red are colors in the graph. So basically the price of daggers, lances, and crowbars are all correlated with each other here in dark blue. So, some of these variables can actually be an issue while fitting, for example, LASSO. So this might suggest that some of these group selection abilities that SuSiE has may be able to help us out for this data set. So now I'll pass the baton over to Amy to take us through the remaining part of the coding.
Thanks for that introduction to the data, Sahid. So for this next part, we're going to start fitting models to our data set. In order to serve as a point of comparison, we're going to be starting off with fitting a linear regression model to our data set to test its performance. So the linear regression model is pretty much the most basic analysis method in the toolbox as far as regression methods go. And so we'd like to see how much better sparse methods do when compared to a good old linear regression. So if we go ahead and run our model and take a look at the results, looking at our first plots, we see that most of our estimates are really close to zero, right along this zero line, but we do have two extreme outliers with our chimera density and our basilisk density that are around -40 and maybe +30. If you recall from earlier, we expect the beta values to be around -1 to 1 in magnitude. So definitely these estimates that are like -40 are wildly inaccurate. So we know that something kind of odd is going on with the linear model. We come over to the second output. This one shows a list of estimated values for each covariate, standard errors, t-values, and finally a column of p-values. Of course, it's kind of hard to take in this long list of values just by looking at it. We have the model telling us that the adjusted R squared value is about 0.73. So we may think that maybe the model is doing well, even though some of the estimates are off base. Let's go on to look at a plot of the estimated beta values versus the true beta values. So ideally, these would run along a one-to-one line. And we can see that for the values where the true beta value is not zero, this is pretty accurate. Unfortunately, though, for the beta values that have a true value of zero, we do have quite a number that are over or underestimating the true value. So that's what this big vertical line is here near the true beta value of zero mark. This plot has even cut off the extreme outliers, but even without them, we can tell that the model is not doing the best job when the true beta value is zero. So now let's look at a final way to visualize the output. A violin plot comparing the estimated values of the covariates that we know are strong with the covariates that we know are weak. We would hope on average, right, that our strong covariates are going to have way higher values estimated than our weak covariates. But unfortunately, that's not what we're seeing here. So many of our weak covariates are being estimated as stronger than our strong covariates. And this tells us that the linear method leaves a lot to be desired. Now that you've seen the linear model, let's move on to the LASSO model fit. Before we fit our model, we need to decide what value we want to use for lambda. That is, how much should we penalize our regression against having large beta estimates? Before going on to the next step, where we determine a value of lambda using cross-validation, let's take some time to consider activity 2. What happens when you try different lambda values? Sure, we show you how to choose lambda below, but what would happen if you used different values of lambda? How would increasing or decreasing lambda change the number of parameters selected, the estimates of those parameters, and the predictive ability of the model? Try to make a prediction before trying it, and then see if you are right by trying a few different lambda values. What happens if the best lambda value is kind of weird, either really low or really high? What would you do? All right. Now let's go ahead and run our cross-validation to select the best lambda value. So we can see here in the first display that we've determined that our best lambda value is 0.02. Now let's examine our cross-validation plot. we can see that the minimum lambda value was here around e to the minus 4. And then over here around e to the minus 2, what it's showing is the largest lambda value within a standard error from that minimum value. So keep in mind here that this is a natural log scale. This larger lambda value might be useful if we want to reduce the model complexity as much as possible. Then these numbers along the top of our graph are telling us how many covariates the model has selected at each value of lambda. So you can kind of see how complex your model will be by looking here. Great. So now that we have our selected lambda value, let's go ahead and run our LASSO model. So you can see here the number of covariates that were selected and their numbers. And also we have our deviance value, which is roughly analogous to an R-squared value, 0.76. So meaning this can go from 0 to 1 and can be interpreted as how much variance approximately are we explaining. So Grace, we're explaining about 76% of variance, which seems pretty good. But what would be more helpful is to visualize the results. Okay. So the first thing that I notice here, compared with a linear model, we have fewer issues with the extreme outlier values. Though we do have this one outlier estimate, it's only at about -3, which is much less extreme than the -40 that we had with the linear model. So it's definitely an improvement. So just so you understand, these blue diamonds show us the true beta values, while the black circles show us the model estimated values. So when our black dots show up exactly within the blue diamonds, we know we've done just about perfect for estimating that beta value. Unfortunately, some of the estimates are 0, which leaves these blue diamonds empty. So the model's, it's not doing a perfect job. Next, let's look at the true beta values versus the estimated values for the LASSO method. So the first thing I notice here is that we don't have that huge stack of values here at true beta value of 0. We just have this single outlier. So the LASSO method is really doing a lot for us in terms of reducing this issue of outliers when beta is 0. You can also see that many of our values do fall roughly around this 1-to-1 line, which means that the LASSO method is predicting them pretty well. However, when they don't fall in the line, you can see that they're mostly above the line on the left and below the line on the right, which is showing us that they're being pulled towards 0, which is one of the risks that we have by using regularization. So we can see this one compares the strong covariates with the weak covariates. You can see that overall, the LASSO method has stronger estimated values for the strong covariates, except for this one kind of outlier. The weak covariates are mostly estimated to be pretty small. So that's a big improvement from the linear model. Now let's take a look at the SuSiE model fit. But before we run the model, let's take a moment to think about activity 3. So SuSiE, it takes in this parameter called L, and L is by default set to be 10 and gives us the maximum number of non-zero effects chosen in our model. So let's think about what happens if you try different L values. We chose to keep the default L equals 10 for this analysis, but how sure are we that that's a good choice? How would increasing or decreasing L change the number of parameters selected, the estimates of those parameters, and the predictive ability of the model? Try to make a prediction on your own before trying it, and then see if you were right by trying a few different L values. SuSiE, unlike LASSO, does not have a built-in cross-validation function for selecting an L value. Could you think of a way to search systematically for the best L value? All right, now let's get into fitting the SuSiE model. Running the model itself is quite simple, just one line of code. And now let's look at what results we get by using the summary function. So the main result is a table here that shows us which variables show up in which credible sets, along with their posterior inclusion probabilities. So you can see that this CS means credible set, and that there are, looks like 7 credible sets in our model. You can see that most of the credible sets have just one variable. For instance, credible set 1 just selected variable 11. However, some of the credible sets, like credible set 7, actually have many different covariates selected. Here's a summary of the 7 credible sets, and you can see only 3 of them are using that group selection. The other 5 just select one variable. Okay. We can also look at this display of the posterior inclusion probabilities, or PIPs, calculated by SuSiE. These tell us the probability that a certain covariate will be included in the model. So if the value is 1, like here with the price of gold, SuSiE is telling you basically 100% this covariate should be in the model. Meanwhile, UV radiation, the probability is like 10 to the minus 9. So the covariate is very likely not going to be included in the model. We can also look at our R-squared value here, which is 0.73, fairly similar to our linear model and our LASSO model, maybe a little bit less than LASSO. So this next block is going to help us visualize the SuSiE model output. Let's go ahead and run it. And look at the first plot. This first graph is the PIP plot, showing the posterior inclusion probabilities on the y-axis and the covariates along the x-axis. Then the colors group variables into the different credible sets. So you can see the pink and the yellow are their own credible sets, whereas the light blue and the darker blue are credible sets with several covariates. Next, let's look at the estimated values in these black dots against the true values in the blue diamonds. Again, when the black dot appears inside the blue diamond, we pretty much have a perfect estimate. So here we have the price of gold and the sunflower density are essentially estimated perfectly in this model. And we can see there is this weird outlier. For some reason, it's the unicorn density again, because as we know, unicorns are special. And so SuSiE helps with our outlier problem. The unicorn density is only estimated here at minus 0.5, whereas it was about minus 3 with our LASSO method. And then, of course, our linear method had estimates that were outliers that were like minus 40. So SuSie's doing a pretty good job taking care of these outliers. Next, let's look at the plot of the estimated values against the true beta values and how they fall along a one-to-one line. So you can see that some of our estimates fall along this line, But there's also many values that fall closer to 0 than on the one-to-one line. For instance, above the line on the left and below the line on the right. So you can see that SuSiE is actually estimating a lot of these stronger covariate values to be 0, unfortunately. Next, let's look at our violin plot of the stronger versus the weaker covariates. We can see that in this case, it looks like we are really doing a good job with the strong covariates because they really are a lot stronger than the weak covariates. SuSiE is very good at not picking any of the weak covariates. It just has this one single outlier. So it's kind of hard to tell from running them once which model is the best model. So in this next section, we're going to compare the different models in their predictive abilities using a simple method. In this method, we'll just split the data into a training and a testing set, randomly choosing a quarter of the data to hold out as our testing set and using the other 3/4 as our training set. Then we'll fit a model to our training set with trying all 3 different models, and then test those fitted models on the 1/4 of the data set that we're reserving for testing. We'll then evaluate the performance by looking at the root mean square error between the model predictions and the true values. Let's go ahead and run it. So you can see, looking at our raw root mean square error values, that the error for the linear model is over twice as high as for the LASSO and the SuSiE models. And the LASSO model is maybe doing just a slightly better job with this lower value here than the SuSiE model. Of course, we may not be sure that this is 100% accurate because we split the data set up randomly. So maybe it would be better if we did that multiple times. This brings us to a tool called cross-validation, which we can use to see how well a model is performing by splitting a data set into training and testing sets multiple times. Today, we're going to be using the k-fold cross-validation method, meaning that we split our data into k different subsets. We then use one of our k subsets for testing and the other k-1 subsets for training. And then we continue on with all k of our subsets, meaning that we will be doing a total of k tests of our data. Keep in mind that there are many other techniques that we can use for cross-validation, but this is just one of the simple ones that we're going to try out today. Before we begin, let's spend a few minutes thinking about activity 4. What happens if you change the number of subsets k that you use for cross-validation? Do you think randomness would affect the results more or less when you increase or decrease k? Is there an upper limit for k? Can k be too high? And are there other ways to do cross-validation that you think could work even better? As a bonus question, think about why some beta values are poorly recovered across all methods, while some are more easily recovered. Do you think there's anything that we can do about this? All right. Let's go ahead and run our block of code to do the k-folds cross-validation. And let's look at our plots here. Our first plot is showing a violin plot of the prediction root mean square error for each method. So you can see that across all of our k-folds, the linear method continues to have a much higher error than the LASSO and the SuSiE methods, with, it looks like LASSO has probably the lowest average error. These next plots show the true beta values in the blue diamonds, and then show a box plot of the distributions of the model estimated values of the other betas across all k-fold iterations. So you can see the linear model still has these two outliers, and they are super variable. So in some k-folds, they're estimated at like -10, and other ones, they could be estimated at -60 or more. They're very unstable, and their magnitude tends to vary a lot. Let's look at the LASSO model results in the same format. So you can see that a lot of these beta values are predicted well consistently, such as when the entire box plot of the estimations are within the blue diamonds. That means that every time we run a cross-validation run, even though we're doing it k times, every single time we're getting pretty much the same beta value estimate, and that estimate is very accurate. Now, we do still have this one strange outlier, the unicorn density, that's varying a lot between runs. This is definitely a warning sign for you to consider. If the covariate estimate changes a lot between runs, resulting in a large box plot, the estimate may be really sensitive to just a few observations in your data set, and whether this observation appears in your training or testing sets affects the estimate a lot. This could be a message that your data set is not sufficient to estimate this particular beta value. And for the SuSiE model, we also have a number of beta values that are very correctly predicted with these bar plots almost completely subsumed inside these blue diamonds. However, we do have a lot of empty blue diamonds showing that, well, a lot of the strong covariates, SuSiE is estimating them to be 0 pretty consistently. So maybe not the best. Next, let's look at our in-sample R-squared values, which tell us how well our model thinks it's doing for just the data in the training data set. You could see that when we look at the in-sample R-squared values, the linear model actually thinks it's doing very well, right? It has high R-squared values. However, this next plot shows the out-of-sample R-squared values. And you can see that in this plot, the linear model is now doing the worst. This is due to overfitting. The linear model is fitting itself too well to the given data, resulting in worse performance when given any new data. And so you can see that the in-sample R-squared value is quite misleading if you just take it for granted. Don't rely on these in-sample R-squared values to tell you how good your model is. Finally, let's look at the parameter estimate comparison for the strong and weak covariates. So the linear model obviously has the highest beta estimates for both the strong and the weak covariates. You can see that the estimates go way far above the true beta values that max out at around 1. Meanwhile, the estimates for the LASSO and the SuSiE model are much more reasonable. We can see that in terms of the weak covariates, LASSO has more of these kind of anomalous outliers compared to SuSiE, which is harsher and ends up cutting out basically all of the weak covariates. However, this is coming at a cost. SuSiE is harsher and ends up assigning several non-zero beta values to be 0. In the end, the LASSO method is a compromise and ends up with a slightly higher average performance compared with the SuSiE model. Well, that's it. We hope you've enjoyed the workshop. Please check the links in the video description for more information about where to go next if you would like to learn more about sparse modeling.